From games to societies, rules are everywhere. In the universe, there are four basic rules that tell all of the basic particles, outlined in this video, what is the smallest thing, how to move and interact. These interactions determine everything about how the universe works on every scale. So, would you like to meet the fundamental forces? We start with the strong nuclear force. As the name implies, the strong nuclear force, or strong force for short, is the strongest fundamental force. If this force is so strong, where is it in everyday life? Why aren't people, buildings, and planets moved by the strong force? The reason is that the strong force is only strong on small scales. Protons and neutrons are made of quarks. These quarks are pulled together by the strong force. How? The strong force has a weird sort of charge. When you think charge, you think positive and negative, but the strong force has 6 charges. These charges are called colors. They are red, green, and blue, as well as anti-red, anti-green, and anti-blue. These aren't the actual colors of the quarks, it's just the name of the charge. The way that the charges attract is that they try to make white. 3 normal or anti-colors, as well as a color and its anti-color, make white. Since the strong force is so strong, every particle with color must be partnered with others to make white. It is nearly impossible to find a lone quark because the amount of energy it takes to overcome the strong force will create 2 new quarks. Also, because of its strength, the amount of energy between quarks is immense. Through E equals mc squared, this energy gives protons and neutrons more mass than their constituent quarks. The strong force is carried by gluons. Gluons are massless particles that travel at light speed. Quarks can change their color charge by emitting a gluon. The gluon will hit another quark to change its color. Gluons are like photons, particles that carry energy. This is important for the next effect of the strong force. You may have heard that the strong force keeps protons from repelling each other in atom nuclei. How is this possible if all protons and neutrons are chargeless in the strong force? This is a side effect of the strong force. Remember anticolors? These are the colors of antiquarks. A quark and antiquark can make a meson, which is an unstable particle important to this phenomenon. Gluons have the ability to split into a quark and antiquark pair because they are made of energy. Remember E equals mc squared. How does this all relate to protons and neutrons? Like this. 1. A quark releases a gluon that excites another quark and causes it to leave the proton. 2. This causes the other quark to release a gluon that splits into a quark-antiquark pair. 3. The new quark stays in the proton while the antiquark pairs with the original quark as a meson. 4. The meson goes toward the neutron where the antiquark and a neutron's quark annihilate, releasing a gluon. 5. The quark from the meson fills in the neutron's missing quark spot, putting everything in balance. This process, also known as residual strong force, works the other way around with protons shooting mesons at neutrons, and it keeps protons and neutrons bound together. The reason that bigger atomic nuclei aren't stable is that this residual strong force only works over short distances. If the protons and neutrons are too far apart, the mesons will decay before getting to each other. In summary, the strong force keeps quarks together in protons, neutrons, and mesons, as well as keeping protons and neutrons together in atomic nuclei. The next force is electromagnetism. This force is the second strongest force after the strong force. While electromagnetism is weaker, it has a larger range than the strong force. Also, while the strong force affects only quarks, electromagnetism also affects some leptons. What does this force do? Look at the name. It is the force of electric charge and magnetic poles. It actually unites these two phenomena. Quarks have either 2/3 charge or negative 1/3 charge. These charges don't do anything inside protons and neutrons because the strong force overpowers electromagnetism at this scale. However, electromagnetism starts taking hold in big atomic nuclei. In the uncommon helium-3 isotope, one neutron is able to hold together 2 protons indefinitely. In gold, the 79 protons are only stable with 118 neutrons holding them together. Clearly, the residual strong force is weakening at large scales. After lead, the 82nd atom, all other atoms are unstable. Of course, the atoms in the 80s will still last for billions of years, while the ones over 100 can't last for more than a second, but they are all still unstable. Electromagnetism is able to beat out the strong force because protons have a positive charge and like charges repel. Electromagnetism makes magnets work. As an electric current moves in a circle, a magnetic field is generated perpendicularly from the center of this circle. Since electrons orbit an atom's nucleus and moving electrons are an electric current, a bunch of atoms with aligned electron spins can make a huge magnetic field, also known as a magnet. You can also wrap up a wire and run electricity through it to make a magnetic field. Because electricity is just moving electrons, this magnetic field is called an electromagnet because it's made by electricity. Not only can moving electricity make magnets, moving magnets can make electricity. Take the generator. The spinning of magnets generates usable electricity. How does electromagnetism work? Photons. Yes, light is just the carrier particle for positive and negative charges, as well as north and south poles. You may think of electromagnetism as a constant pushing rather than a single push, and in a way it is. On the quantum level, an infinite amount of photons can be exchanged between the charged particles. This is just the weirdness of wave-particle duality. A smooth wave is interchangeable with an infinite stream of particles. Overall, electromagnetism is the force of electricity and magnetism. It works on the macro and micro scales as a major force. Come back next week to meet the other two fundamental forces and to learn of their shared past.